So most of my friends here spoke about big data and extreme computing. They're all coming together, and there's a clear role for burst buffers. And people also spoke a bit about non-volatile memories. So this project sort of puts everything in one picture. So it might answer some of the people's questions as well in terms of how everything comes together, how the non-volatile memories, play a part in the storage hierarchy, and things like that. So the consortium consists of 10 partners, so led by Seagate. So interestingly, we've got some of these partners are extremely large data generators. For instance, you have Diamond Light Source, which is a UK-based organization. You've got CCFE, which is the Column Center for Fusion Energy. So some of these partners we have in the project are very large data generators. So we are looking beyond traditional computing simulation codes. We are looking at partners that can actually bring in extremely large data sets as well to actually help us co-design the storage system. So I'm going to talk a bit more about what everyone is doing and what's Seagate's role and what are we actually bringing to the, what's innovative about the project, and especially the focus is on the software innovation around building a next generation object storage software technology that can work with a wide variety of use cases very flexibly, which has a very flexible API and things like that. So this is a 9 million, this is a 8 to 9 million euro project. So started in 2015 September. So it's going to go on until 2018 September. So I don't have to repeat this. It's so storage cannot keep up with compute. It's quite clear, and there's way too much data, and the main point is there's way too much energy required to move the data to storage. So so everyone is so focused on reducing the energy requirements, but what we really need to understand is moving the data to compute takes about 100 times more energy than keeping the data in place. So when we try to build all these exascale systems and everything, we should really try to understand what are our parameters, where are the knobs for controlling that energy energy metric. So if we can think about ways to control this, reduce this movement of data between storage and compute, that will be, that's what we as storage, as a storage technology, providers really need to think about. And I'm sure some of my colleagues, some of my friends from the other organizations clearly understand the value of not moving the data around, especially when we are looking at very large scale systems. And the other aspect is everyone's talking about non-volatile memories. So let's think beyond flash. We have storage class memories. We've got phase change memory or 3D crosspoint, or we've got all sorts of RAM and STT-RAM. People were talking about so many different kinds of devices. There is some early numbers, in terms of how these devices perform and stuff like that, but we have not seen a lot of these things in the market yet. But how are we actually going to use them in the I/O stack? It's not very clear. So we can say, okay, you can actually use it as memory, or whether you use it as part of your I/O stack, or part of your storage stack. So things are not very clear. At least with the Sage project, we want to start exploring those sort of capabilities of these kinds of devices as part of a system solution. The other opportunity that we want to explore is this overlap between big data analytics and extreme computing. I don't have to harp on it again. I think all of you, by the end of the day, it's really quite clear that there needs to be infrastructure that can combine big data analytics workloads as part of extreme computing, especially in the realm of HPC, because there are workflows that has very large data sets, and the workflows have simulations as well. So everything needs to come together. It just doesn't make sense cost-wise to have two different infrastructures, one for big data analytics, another for extreme scale I/O. I mean, it really makes sense to actually have a converged infrastructure. I mean, that's quite obvious by now. So the goal for the Sage project is essentially look at this overlap between extreme computing, which has changing I/O needs, of course. People are talking about there are going to be simulations generating extremely large amounts of data, and hard HDDs cannot keep up. The hard disk drives cannot keep up. So it's quite obvious that we started with burst buffer solutions and everything because you have to somehow close that gap. And then there's a massive, I say massive data analysis because it's just so it's just avoiding data movements and somehow to manage and process extremely large data sets very close to where without moving the data. So there's some overlapping requirements. So the idea of the SAGE project is to build this BDEC system. BDEC is the term that has been introduced by our friends from the BDEC work group, which is very good that we have a terminology to speak about these kinds of systems now. So the idea of the SAGE project is to build this BDEC system that can actually ingest and store and process and manage these extreme amounts of data as a single storage solution. So classical storage solution is just takes the I/O from the simulations, just stores it, just reads and writes data. But when we look at the whole workflow where you ingest and store and process and manage everything as part of the same storage solution, we want to explore that in the SAGE project in the context of exascale storage and extreme scale storage systems. So the big vision for us really is to try to look at this big workflow. So there is a supercomputers that generate extreme amounts of I/O. But we also look at this workflow where we have these extreme data generators as well. It could be the CERNs or the square kilometer arrays, or it could be any of those big science experiments, or it could be industrial data, sensor data, or anything. I mean, you need all this data. You need the simulation output as well to actually, for holistic science. So look at all these data sets. That data needs to be pre-processed, post-processed, transformed, visualized, and you probably want to do predictive analytics and data mining and stuff like that. So all these insights and discoveries from all these data sets need to be somehow fed back into running simulations. So that can actually really enable you to develop, generate better science. And the point is to get to quicker time to solution. So it's not just about parameters like I/O throughput or latency or jitter, or there's so many parameters and knobs you can play with. But the idea is to generate faster science, get to quicker time to solution by building systems that can actually do that would be absolutely valuable to the community. So the overall objectives is to provide a novel storage architecture. So that's going to be based on a object storage technology, software technology called Miro, M-E-R-O. So we used to keep it under wraps, but now it's more open information. There is some publications as well. There's some presentations. You can have a look at it. So right now it's a proprietary object storage software solution called Miro, which drives a multi-tiered storage system. So it's not just a burst buffer and hard disk drives and an archive, but it's a multi-tier. I'm going to talk about what this multi-tier is. So I spoke about increasing overall scientific throughput. And the idea is that with one project, we cannot hope to solve all the problems for storage and I/O. But what we want to do is learn along the way from the use cases and develop these component technologies that we can take forward. So we don't promise to boil the ocean or anything, but at least we can learn about the use cases, what's actually required, and build these pieces of technology that we can actually take forward on the road to exascale, so to speak. So it's all about building a next generation multi-tiered storage system, which I'm going to talk about in the next slide. So as part of building that, building the software solution for driving this multi-tiered storage system, so it needs to work hand in hand with a lot of ecosystem components. So just as a storage solution provider, we can't just hope to build some technology bottom up and hope that it's going to solve all the problems. So we have to work very closely with the use case community. We have to look at programming models, programming techniques. We have to look at existing data management techniques. And we have to look at what kind of optimization tools exist today, debugging tools, and what kind of next generation storage media are people really talking about, what's really practical. We need to look at all these kinds of issues, and what's the extreme data analysis. I mean, you have Hadoop and Spark and Flink and whatnot. So, I mean, given the state of the ecosystem, I mean, what kind of a storage system can you actually build and deliver something which is, practical? So we are looking at all these areas of research as part of the SAGE project, as sort of an ecosystem around the core storage system. So this is the storage system. It's a 100,000 feet overview. So as you see, it's a multi-tiered storage system. It's not just flash and drives. So it's going to have all the tiers, starting from memory to different pools of non-volatile memories, having different characteristics. And it's going to have somewhere in this hierarchy, there's going to be drives as well. And there's going to be archival grade. We don't look at tape, of course. It's all disk is the lowermost tier. So it's a multi-tiered storage system, which has inbuilt compute capability. So you don't have to move data sets from the storage system to the compute. So you can do in situ computation. So we have provided these embedded compute modules very close to the storage system. You can do compute capability very close to these tiers. So as you go up the hierarchy, the compute gets more and more dense, because of course access latency is reduced as you go high, and you have to do more computations as you go up the stack. So that's why it's an inverted triangle. So as you go down the tiers, I mean, if you come to the scratch storage and archival, you just want to use it as a dump. You probably don't have to do a lot of processing when you get to the archival state. So this is compute capability very close to these tiers. And at the top, so this object storage infrastructure is what I termed as Miro, M-E-R-O. So it's at the top, it has a very flexible API. And the API is called Clovis, C-L-O-V-I-S. So the API is capable of working with existing codes, existing simulations. Has it has a key value store, object store, basic object I/O. I'm going to talk a bit about the capabilities of Clovis as well. And the Clovis API can be used to actually to ingest all these big science data sets from the cloud or from anywhere else as well. So it's a unified API that actually talks to the storage system. Just mind you that we are not inventing any hardware. So we use whatever hardware exists. So I quote unquote commodity hardware. We work with the vendors to see what's coming in the roadmaps for all these non-volatile devices. I mean, because it's a software-based, it's an object storage software solution. We should be able to work with a wide variety of device hardware. So yeah, we just use commodity components, so to speak. We of course use some of our Seagate enclosures in the project. So where it's very optimized for for Seagate enclosures, of course. So what are we actually demonstrating at the end of the day in the SAGE project? We use SAGE as just an application I/O box, like what's done in this, what's done today. Or we could use the SAGE system as an offload device where you can pick some parts of your compute, see which is very data-centric, and actually offload it to the storage system so that some parts of your application works in parallel with some parts of your code that runs close to the storage system. So you can actually reduce your time to solution. Or you could do a full data-centric offload. If you can parallelize your pre-processing and your, if you can parallelize, if you have some parallelizable aspects in your workflow, like pre-processing, post-processing, you could actually run that in parallel with these computing tasks. So we will eventually demonstrate a fully data-centric mode as well. So with all the use cases that are there in Sage, we eventually want to demonstrate these 3 modes of operation. I'm going to talk about when and where and stuff like that as well. So this is a bit more technical. I'm not sure if, hopefully you can get some idea of it. I'm going to talk through this anyway. So at the bottom in the black is your compute hardware. So which is these multiple tiers from non-volatile memories to flash and disk. I say DRAM here. We are just exploring that. So it's we are not seriously, we are still not using DRAM as one of the tiers, but for object storage. But it's something we want to explore. So we start with NVRAM, flash, and disk with inbuilt compute capability at the bottom, which is the system hardware. Going one layer up is the object storage solution called Miro. It's just above the black. So what Miro has is, don't worry if you can't read it, I'll just talk through these things for you. So what Miro is essentially a key value store and an object I/O handling at the bottom. So this is whatever you get in existing object storage solutions like OpenStack or Ceph or whatever you want. So we start with the basic object store. So that's where we started off with Miro. And then we looked at what are the possibilities, what are the features that needs to be developed within object stores to get it ready for the next big leap in for HPC and BDEC. So some of my friends spoke about all the issues about existing parallel file systems and stuff. So on top of the basic services that's offered by object stores, like a key value store and an object I/O, we are building all these nice components, like containerization and advanced resource management. So there's a bunch of blocks on top. So it's layered on top of a basic object store. So it's about things like how you can deal with so-called layouts. So layouts is a feature by which an object can be layered across multiple devices. So you have an object in the front, and the back end, a part of an object can be in non-volatile memory, a part of it can be in flash, a part of it can be in Scratch. So based on how the application is actually using it, you dynamically keep changing the layouts based on how the application uses it. So that's one very interesting feature that we are building in Sage. And the other is, of course, I think some of my friends spoke about transaction management as well. So I don't have to go that. It's extremely important to actually batch I/O requests, especially at scale. You have to think about how you can manage all these distributed transactions. And then containerization. So you have so many data sets. You have HDFI, NetCDF, POSIX. So all of these different data sets, different applications, they have different requirements. So how can you actually virtualize and tag all the objects corresponding to how it's being mapped to all these different data sets and use cases. So that's what is called containerization. And then we've got advanced resource management is an internal aspect of how you can actually do peer-to-peer caching and locks and how you can deal with all these kinds of things when you have these multiple tiers. And then we have function shipping. It's a feature of the object store which is capable of accepting computations from the application or from any tool. So you accept the computation and you run the computation in situ in any part of in any tier of your stack. And then we've got advanced views and schemas. So essentially what we do is for the same set of objects, you don't have to copy them. You have the same set of objects, but you can have a POSIX view or a HDFI view or a NetCDF view or any view that you like without copying the objects. So you just manipulate the metadata. So that's why we call it advanced views and schemas. So that drastically reduces your infrastructure load on doing this kind of things. So and of course, at exascale, the failures are going to be a norm. It's not going to be an exception, and you have to build a very highly available system. So we are building a very highly available infrastructure around Miro that's capable of handling faults occurring very frequently. it's based on consensus protocols and stuff like that. So that's Miro. That's the object store Miro. So going one layer higher, on top of Miro is the API for accessing Miro. It's a very flexible API, so you could actually just use Clovis to do key value store and object IO, which is the access interface. I'm going to talk about how the applications actually use Miro, because Miro is quite low level. You have an extension interface where you can actually pull operation logs from the storage system. And you have a management interface which actually pulls all the telemetry records in Miro. So one of the things that we learned while developing Miro, and mind you that Seagate has one of the best Lustre developers, one of the early Lustre developers who were all involved in early Miro development. So they've learned a lot. We have learned a lot about the issues with Lustre, and especially it's so difficult to look at the logs and try to find out performance problems and stuff like that. So with Miro, we have structured telemetry records from the ground up. So everything is very structured. You could easily do sort of analytics on top of the telemetry records to find where the problems are, which point in the stack is giving you the problem. You can do request path analysis. So you can do all these very interesting things with the Miro telemetry. So there's an interface to access that telemetry data. So that's the Clovis API. So you have basic object IO and the extension interface and the management interface. So how is it actually being used? How is it used by the world? So for the access interface, so the question is, how do POSIX applications, how do they use Miro? How do HDFI datasets use Miro? How does MPI-IO use Miro? So to answer these questions, we've got so-called gateways on top of Miro. Very easy to build. You have to build these kind of connectors on top of Clovis, because Clovis is a very low-level construct. So you have a Flink connector for data analytics. You can have a Spark connector if you like. And you can actually overlay POSIX, a POSIX namespace, as Jacques Charles was mentioning some time ago. So Jacques Charles, CEA, is doing some really interesting work in trying to actually superimpose a POSIX namespace on top of Miro. So the CEA is looking at building a PNFS layer on top of Miro. Very interesting work. And also you can use, if you want to use HDFI datasets, so you could actually build a virtual object layer that talks to Miro. So you use existing infrastructure within HDF itself to talk to Miro. And within the project, we also have MPI-IO over objects as well, which is another plugin on top of Miro. And the other interesting piece of, I should say, slightly earlier stage research is how to explore PGAS on top of Miro. So interestingly, so Miro has all these tiers, right? It has non-volatile memory and everything is, you have all these pools which you can access. So we started thinking, oh, why don't we actually make it part of the global address space itself, you know? So it might have some very interesting connotations, especially with PGAS languages and stuff. So you could use some part of the top tier of the Miro storage as part of your extended PGAS address space. So we are actually looking at that as well, which is exploratory, fun, interesting type of work. So so for the tools, so for tools we have Alinea performance tools, and we've got HSM tools and data integrity checking tools. They're all plugins on top of Miro. So Miro has a so-called plugin interface, which is the extension interface. So all these tools and everything they can just be plugins on top of Miro. You could build your own plugin. Third parties can build their own plugin. So this, in a nutshell, is what we are doing in the Sage project, and we are doing runtimes as well. So where you actually directly use the hardware. So in case you want to explicitly use these tiers and you don't have time to request the HSM engine to do your data movement and everything, or if you don't have time to go through Clovis, you can just explicitly get access to all the tiers directly for visualization or anything like that through the runtimes. So this, in a nutshell, is the top-level technical architecture of for the Sage platform. So what kind of applications are we looking at? We are looking at satellite data processing, bioinformatics, space weather, nuclear fusion, and these extreme data generators like synchrotrons. We've got all these kind of use cases in the project. And we've finished this first phase of co-design with the use cases. And we have a good handle of what are the scaling characterization, what's the scaling requirements of all these use cases. Because all the use cases that we have is something that are brought into the Sage project with a view of how they would actually scale out going forward. So all these are codes that are going to drastically scale their I/O needs. So we completed this work, and I just spoke to you about Miro. So one point I want to mention is that our partner Atos is doing very interesting work, looking at non-volatile memories. So I spoke about so many of these different types of NVM device technologies. So they're systematically looking at what can be brought into the Sage project, what's available in the existing roadmaps, and because we started very aggressively saying we are going to look at this very big multi-tiered system, but now we realize none of them are in the market, and many of them are just gone, and we have to work with what's there, and Atos is looking at very interesting ways of emulating these devices within memory. So yeah, I mean, we're looking at, in terms of tools, we're looking at HSM, PNFS, and data integrity checking at extreme scales. We have completed all the design work and the architecture work, actively working on implementation. So Alinea is working on their performance tools. So I mentioned to you about MPI-IO and PGAS and things like that. So the idea is to build this system. So this is the actual picture of the Sage system. So it's just one system. On the left side, you have, so the system is going to have 4 tiers. Left side, you have the green boxes is from our partner Atos. That's the tier 1, the topmost tier, compute dense, non-volatile memories. Second tier is SSDs. Third tier is going to be traditional high-speed disks. And the last tier is going to be archival grade disks. So these are the 4 tiers, and we have completed the build of this just as of last week. And it's already shipped to Ulic. So in Ulic Supercompute Center, we are going to actually connect it to their cluster and work with the actual use cases. So that's going to be the highlight for the next 18 months of the project. So this is how the system looks like just before it's shipped. So yeah, I mean, it's shipped now, month 18, so everything is on track. We'll complete all the designs. So look for some results coming from the Sage project in the next 18 months for all these different tools, all these use cases. We may not have built an exascale storage system, but at least we would have learned a lot about what it really takes to get there. So yeah, I mean, I don't have to go through this once.